Okay, let's unpack this. Today, we're going to dig into some really core concepts for enterprise wireless networks. WLANs, if you're involved with, designing, deploying, maybe just managing Wi-Fi in professional settings, this stuff is pretty fundamental. We've got some interesting source material today. It's actually drawn from practice questions and the explanations that go with them related to the CWDP-305 exam. That's a certification focused, squarely on enterprise WLAN design. So our mission here in this deep dive is basically to grab the key insights from this specific source, kind of distill them down, and help you get a quick handle on some critical principles, things that pop up again and again when you're working with wireless. Think of it as a shortcut to some key design thinking.
Right. And that source material gives us a pretty specific lens. Just for context for everyone listening, the CWDP-305 itself, it's a proctored Pearson VUE exam, typically around, 60 questions? Something like that, hour and a
Yeah,
half.
about 90 minutes.
And you need 70% to pass. It's delivered in English. So the points we're exploring today, they're framed within that body of knowledge. Stuff considered essential for, professional WLAN design. We're pulling directly from how these ideas are presented there.
Perfect, yeah. Understanding the context helps frame why these specific points get highlighted. Okay, let's jump into the first one. Something really critical when you're planning Wi-Fi for places packed with people. Auditoriums, big conference halls, you know the type. In these high-density spots, the source material really hammers on one factor being absolutely critical. What is it?
The thing the source really stresses, above all else for high-density design, is limiting the number of SSIDs being broadcast.
Limiting SSIDs. Okay. Sounds simple enough on the surface, but why? Why is reducing the number of network names so vital when you've got potentially thousands of devices around? What's happening under the hood?
Well, it really boils down to airtime efficiency. You see, every single SSID and access point broadcast needs management frames, mostly beacon frames.
Beacons, right.
And these beacons, they're sent out constantly, usually about 10 times a second per SSID, announcing the network. Each one eats up valuable airtime. So the more SSIDs you pile on, the more beacons are flying around. And that adds up fast, especially in a crowded place where airtime is already, super valuable. This beacon overhead, it basically cuts into the time available for actual user data. It just increases channel use with management traffic. So by limiting SSIDs, you drastically cut that overhead. You free up airtime for clients to actually communicate, which improves performance, capacity, and the whole user experience, really, in that dense space. It's like one of the quickest wins for a high-density network.
Wow, okay, so it's definitely not just cosmetic. It's a fundamental drain on the very resource everyone's trying to share, the airwaves. The sheer number of SSIDs directly hits the capacity left for real work. That's a really key takeaway. Knowing how broadcasting too many SSIDs can cripple performance, particularly when things get busy. All right, let's shift gears a bit from density planning to understanding the environment before you deploy anything. Site surveys. The source material highlights a specific type, the passive site survey. What's the primary goal? What are you trying to find out when you do a passive survey?
According to the source, the main goal of a passive site survey is to detect existing RF interference and also neighboring wireless networks.
Okay, interference and neighbors. How does a passive survey actually do that? What makes it passive?
The key thing is with a passive survey, your tool, your laptop, your device, whatever, it's only listening. It's not transmitting any signals itself. It just scans the radio spectrum to hear what's already out there. This lets you pick up non-Wi-Fi interference sources, things like microwaves, cordless phones, sometimes faulty electrical gear messing with the Wi-Fi bands, and crucially, it also finds all the Wi-Fi networks nearby. Could be your older ones you forgot about, or definitely your neighbors' networks. You see what channels they're using, how strong their signals are, gives you a feel for the noise floor, potential interference, all before you switch on your new APs. It's like scouting the battlefield first.
That makes perfect sense. Yeah, you wouldn't build a house without checking the ground first, right? So same idea for Wi-Fi. You got to listen to the RF environment, see what challenges are already there. So a passive survey is basically eavesdropping to map out interference and other networks, vital for making smart design choices. Okay, let's move into newer tech now. Pulling another key point from the source, this time about 802.11x or Wi-Fi 6. Wi-Fi 6 brought in several features for better performance, more capacity. One specific feature highlighted lets an AP talk simultaneously with multiple clients on the same channel at the same time. What's that called?
That feature the source is pointing to is MU-MIMO. Multi-user, multiple input,
You're right.
multiple output.
We hear that term a lot with Wi-Fi 5 and especially Wi-Fi 6. How does it actually do that? Talking to multiple users at once sounds kind of like magic.
Not quite magic, but it is clever. It's about using spatial streams effectively. You could think of it like someone speaking multiple languages at once to different people. But instead of languages, it's spatial paths in the RF. An AP with MU-MIMO and clients that support it too can use its multiple antennas to create separate directed data streams aimed at different clients concurrently over the same frequency channel, which is a big step up from older tech where the AP pretty much served one client at a time per channel, right? Yeah. Even with multiple antennas. MU-MIMO seriously improves spectral efficiency, lets the AP serve several users in parallel. This boosts the total throughput, the capacity of the AP. Super important in places with lots of active users, assuming their devices are also MU-MIMO capable. It's really core to how Wi-Fi 6 handles higher density and demand.
That analogy helps, serving multiple tables at once instead of just one. Yeah. Understanding MU-MIMO seems key to appreciating how Wi-Fi 6 tackles that constant demand for more bandwidth, more capacity. A fundamental piece for getting more out of the airwaves. Okay, so we've designed the network, we've put in the APs. Next big phase, also highlighted in our source, validation. How do you confirm the network you just built actually works the way you planned, that it meets real-world needs? What's the single most important activity for validating that WLAN design?
The source material is pretty direct on this one. Performing on-site throughput tests. That's the most critical validation step.
On-site throughput tests. Interesting. Why measuring actual data speed? Why is that so much more crucial than, say, just checking signal strength or verifying the AP's powered on?
Well, because signal strength is just one piece of the puzzle, right?
Yeah.
A strong signal doesn't automatically mean good performance. You need to know what users will actually experience when they try to send and receive data. Predictive designs, heat maps, they give you theoretical estimates. But the real world, it's messy. Building materials aren't perfectly consistent. Interference pops up unexpectedly. Client devices behave differently, right? On-site throughput tests measure the actual performance under realistic conditions. They show you the real data rates you can get in different spots. This confirms if your design truly delivers the needed capacity and coverage where it matters. It's really the definitive way to verify the deployment works. And, maybe just as important, find areas where it doesn't meet expectations and needs tweaking, like the final report card for your design.
That's a powerful point. Testing the actual user experience, the throughput, is the ultimate reality check. Brings theory face-to-face with reality. So, key takeaway. Real-world testing, specifically measuring throughput, is basically non-negotiable for validating a WLAN deployment, making sure it works for the people using it. Okay, let's wrap up our deep dive today with one last concept from the source. Moving outdoors for this one. Say you need Wi-Fi coverage for a very specific shape, maybe a long pathway, a corridor between buildings, perhaps even a long track or runway, something long and narrow. Antenna choice becomes critical here, right, for directing the signal just where you need it. What type of antenna does the source say is best for covering that kind of long, narrow area?
The source material identifies the Yagi antenna. It's particularly well suited for those long, narrow coverage zones.
A Yagi, yeah, you see those sometimes. Looks kind of like a fishbone on a pole. Why is that specific type good for a long, thin strip of coverage?
Yagis are known for being highly directional. They have a very focused, narrow beam pattern, almost like a spotlight, but for radio waves. This means they concentrate most of their energy, transmit and receive, in one specific direction, along a pretty tight line. So for a long, narrow area, that's ideal. You point the Yagi down the path, and you can push the signal much further in that direction compared to, say, an omni antenna that just broadcasts everywhere. Focusing the energy also helps cut down on interference, both interference to areas outside your target zone and interference from those areas affecting your signal. It makes efficient use of the spectrum and improves signal quality right where you need it, along that path.
Got it. So antenna choice isn't just about power, it's about precision, shaping the signal for the exact area you need. Knowing a Yagi is the right tool for those long, narrow outdoor jobs, that's valuable practical knowledge.
And, thinking about that last point on validation, where the source stresses that on-site throughput tests are crucial, not just for confirming success, but significantly for finding needed adjustments. It kind of raises an interesting question for you to think about. If even a well-planned design needs real-world testing to find things that need changing, what does that really tell us about the inherent unpredictability of RF environments, maybe, user demands, and perhaps the idea that successful WLAN deployment isn't just a one-shot deal, but more of an ongoing cycle, a continuous process of monitoring, validation, and refinement, something to mull over.